All right, everyone. Thank you for joining today and welcome to the July Building to Net Zero Community of Practice. Staying cool, staying healthy, designing high performance buildings with health and comfort in mind. Before we get started today, we wanted to take just a moment to recognize that ICLEI Canada is joining from the traditional territory of the Mississauga of the Credit, the Anishinaabe, the Haudenosaunee, and the Huron-Wendat peoples. Toronto remains home to many First Nations, Métis, and Inuit peoples today. We would love for you to share in the chat where you're joining from today, including, if you know it, the Indigenous lands that you're joining from. If you're unsure, I'd invite you to follow the link that I just popped there into the chat to Native Land Digital. This maps Indigenous lands while also providing information on treaties and languages. If you haven't checked out this resource or others like it before, I definitely encourage you to do so. As we discuss climate responsive design and building performance today, we're also reflecting on how many approaches central to building sustainably reflect longstanding Indigenous practices. So these might include things like attention to orientation, materials, and relationship to place. So we wanted to highlight the importance of this legacy and recognize and encourage some reflection on how these knowledge systems that can and should be informing our current practices to create healthier and more resilient homes in the communities that all share these lands. All right, so to get started, we're joined by two speakers today, and we're very excited to have with us to share their expertise. First off, we have Dr. Marianne Touchy, an associate professor at the University of Toronto, director of the Building Energy and Indoor Environment Lab, and also Canada Research Chair on sustainable urban housing. So as one of Canada's leading authorities on multi-unit residential building performance, particularly in the social housing sector, her interdisciplinary research explores how buildings can be engineered to improve comfort and health for residents. We're also very happy to have Kara Sloat, a building services focused mechanical engineer with over 20 years of experience in engineering multi-residential buildings. She works at the forefront of advancing low carbon, high performance design strategies for her clients as mechanical principal of Hammerschlag and Jaffe, a Toronto-based practice delivering solutions for buildings right across Canada. Thank you both very much for joining us today. And whenever you're ready, feel free to get started and share your slides.
A warm welcome. I'll just share my screen. Can everyone see that okay? Yep. Okay, great. Wonderful. Okay, welcome. Thanks so much for the invitation. Kara and I are delighted to be here today to talk to you a little bit about health and comfort in high performance buildings, particularly in the context of extreme heat. So let me just get my slides advancing here. So today we're going to cover a few things, talking a little bit about the risks of overheating, and then turning to some real world examples to show you what's happening in high performance buildings and really dig into some of the root causes of why we're seeing some of these performance challenges in the context of extreme heat, and then provide some ideas for some design adaptations that we can consider moving forward to address some of these risks. So I'm sure I don't need to remind everyone in the audience what happened a couple of years ago. It's still, I think, yeah, it's something that a lot of us are reflecting on, and how extreme the impacts of the heat dome was in BC, and even reflecting on the last couple of years. And for those that are in the Toronto area, even a week and a half, 2 weeks ago, we're really, these events are becoming part of our day-to-day lives. And it's something that we've never really considered in such a deep way in the design of our built environment. And so I think the BC heat dome really kind of brought overheating risks front and center for folks. And I think it's important to just think about all of the lives that were so deeply impacted by that event, both 5 years ago and in the intervening period here. And it's not just Canada, it's all over the world. These are things that communities, cities around the world need to address. So when we look at the GTA specifically, and this is just one example, there are cities all over the world, conditions are changing. We're looking at huge increases in our maximum temperatures, extended, more extreme heat events as well that will take us into the future. And this has impacts on how our buildings operate. So of course we'll see decreased heating with a warming climate, but we'll also see increases in cooling with future weather. And this has implications for energy, of course, and I think we often talk a lot about that, but it also has implications for how people experience buildings. So this is just some modeling that we did a number of years ago. The numbers don't really matter so much, but CWEC is the Canada weather for energy calculations. So basically a weather file that represents our historical weather from the past 30 years. And the 2040s weather file represents a projection, and there are many. But we were kind of playing around just to understand, well, if we had today's equipment in our buildings, how many hours of unmet cooling need would we see in some of these future weather conditions? So this is where this exercise stemmed from. But needless to say, we're going to see a lot of more challenging conditions that we need to deal with. And so if that's the impact that that has on buildings, it also impacts people in very different ways. So this is some data, it's actually about 10 years old now from Toronto Public Health, which shows the penetration of air conditioning across different income brackets. And you can see that at the lower end of the spectrum, there is much less penetration of air conditioning, which means that with our buildings, which are fairly ill-equipped to deal with extreme heat, we have a lot of people who just really don't have any escape from that. And these numbers actually get bigger when we look at the rental housing stock as well. So there are a lot of vulnerable folks when it comes to extreme events. So these are, I'm kind of throwing a lot of numbers at you, but it's really important to think about what that experience is for the people who are living in these buildings. Some of you may have seen this. CBC did a piece 2 summers ago called No Escape from the Heat. If you haven't looked at this, I would encourage you to take a look. There's a lot of video blogs of folks who are in housing without air conditioning. And it goes through all of the measures that they take to try to stay comfortable and healthy in their homes. And so it really puts puts a personal face on how people are coping with these. I think we're being bombarded by statistics, but I think it's important to remember that there are people living behind those statistics, and there are real consequences for this. And a lot of people will point to, oh, just install more cooling centers and have those available in every neighborhood. Well, how many people want to leave their home and spend time in a public space in the middle of the night when they're trying to sleep in a cooling center? It's just, in my mind, I think in many people's mind, this is not really a practical solution. And so we can't just continue to lean on this. Oh, we just need more cooling centers. No, we need to do things about our built environment to make sure that we can keep people comfortable and healthy in their own homes. That's not really care.
Yeah, that's right. And as a practitioner, I have felt my responsibility in Canada was to heat buildings. We've spent a lot of my professional career worrying about liability around heating buildings. It's a place where I get a lot of questions from building officials. This exterior room doesn't have a heater. Sometimes there will be closets or like tiny little spaces that I don't quite have the load right. But very few people have ever asked me about cooling. Air conditioning isn't required under the building code. And so it was really interesting to me last year when I was assisting an acquaintance evaluate a heat injury in their workplace to learn the amount of time it takes to be seriously injured or killed by overheating is much, much shorter than the amount of time it usually takes to be harmed by low temperatures. So normal indoor temperatures that are easy to experience in a typical unheated building can cause death in 2 to 6 hours. The Center for the Built Environment has a thermal comfort tool I was very used to using, but it has this extra tab I'd never seen before called the PHS that allows you to evaluate the likely strain for a healthy adult of being exposed to high temperature and humidity. And we found in the building that I was evaluating that, an average person could expect to experience heat injury in 130 minutes. So as a mechanical engineer, as a building owner, as people responsible for buildings, this switch in framework, when I went and looked to try to find who in Canada dies every year in their own home in the winter of being too cold, I actually can't find anybody. So this is a much higher life safety risk than the heating that we've been used to spending time on. And that framework shift has been really important for me and kind of frames everything you're going to hear from me in the next hour. So it becomes even worse when I realize that high performance buildings are improperly protected from these issues, and in some cases, more vulnerable to overheating than the traditional buildings that I work on that didn't have high performance goals. So when we started to realize this, we started to ask ourselves, why, right? Yeah, why? So the more we dug into it, you'll see a case study about one of my buildings that overheated later in this presentation. We realized that it was caused by a number of different factors. We've grouped them into 5 major families. So, sort of planning issues and the architecture of the building, beliefs that we as designers and building owners held about the building, issues about our misunderstandings of what a system typically does, but also what we can expect if something breaks. And then the behavior of the people in the building, understanding how people interact with those buildings in real life. So, uh, the first and biggest thing that we've really lost as a culture is to, next slide, sort of build buildings that work without active air conditioning. And again, it's because we're used to thinking of our environment as a place where heating is important and cooling isn't. But climates that have often had significant air conditioning requirements were designed with multi-story spaces, high openings for stack effect and wind. It's all right. Spaces where you have shade created. This example that you see on the right-hand side of this slide is one of my favorite sort of Canadian buildings. This is the architecture school in Cambridge. It's a factory. So it's an old factory, and it's got this sawtooth roof on the top floor that's letting natural light in. So you don't need to have any active luminaires in the space overheating it. It's also not letting in direct sunlight. So the sunlight's blocked out, the light itself is getting in, and you've got this high space where heat can rise to the top and escape. So this building, when we have a power outage and the air conditioning goes down, is more likely to remain occupiable. And now we can flip the slide than this really typical multi-unit residential building that looks like, a lot of the high performance buildings that we often see written up in magazines. So we're blocky, we have very low window to wall area. We don't have a lot of openings. We don't have any overhangs on our exterior envelope. We've got often views that are highly influenced by the site. So a lot of east and west glazing because our cities are set up to allow that. And because we're trying to maximize the number of suites we can get into these buildings. And so, and very little in the way of thinking about how we could use deciduous plantings to be able to add shade or reduce urban heat island effect. And we sort of combine all of that stuff together, and we end up with buildings that are really good at overheating, just as much as a code compliant building, sometimes worse or more. And we are also in Canada afraid of exterior shading, especially the movable kind, which keeps almost all of the solar heat gain out of the space. So if you're using an interior shade, you've already let the heat in through the window. So you've got this really hot air gap between your interior shade and the glass. And you're also creating kind of a doom and gloom environment, which to a certain extent, these exterior shades do too, but like an exterior horizontal overhang, again, gives you light and views while keeping direct sunlight out. We're especially unlikely to use exterior shading, I believe, because of our freeze-thaw cycles. So we're just afraid of the wear and tear due to our climate. But we do have a lot of problems that we therefore are creating for our buildings by having these plain walls with south, east, west facing windows, letting in a lot of light. And then, next slide, in our well-meaning search to create high performance buildings, we've encouraged high solar heat gain windows by creating a new metric we called the TEDI, the Thermal Energy Demand Index, which is how much energy over the course of a year a building needs for heating. And so we created a maximum on that, and you can just drive that down by increasing the amount of solar gains in the space. We don't have an equivalent SETI, so cooling energy demand index. So there's no control in this high performance building metric that discourages designers from creating overheating spaces.
So Karen's done a great job of kind of setting up all of the things that we're missing. So maybe let's talk a little bit about some of the things that we can add to our buildings to try to prevent this overheating. So there's really a couple of different bins that we want to consider. So passive measures, what I mean by that are things that don't require any energy to use. So these are just baked into the building enclosure. So reducing those solar gains and ideally trying to promote free cooling, nighttime cooling where possible. So I'll discuss those in a little bit more detail. And then once you've kind of done all you can on the passive side of things, then maybe you kind of reach for some active solutions to get you the rest of the way there. So we'll talk a little bit about those as well. So from the window side of things, as Karen mentioned, we're trying to get as many free solar gains to offset our winter heating load as possible, like we see on the left-hand side. So we typically see very high solar heat gain coefficients that are specified for that reason. But that is obviously to our detriment in the summer because we're letting in all of those solar gains that we then need to get out through air conditioning or other needs. So moving towards something that we see maybe more on the right-hand side with a lower solar heat gain coefficient. Yes, there are trade-offs with the winter gains, but we can really do a much better job at controlling those solar gains in the summertime when it's often more difficult to get rid of that heat. And shading. Kara showed one example, where we've got all the windows covered. It kind of looks like a bit of a bunker, but there's so many different ways that we can achieve exterior solar shading in lots of architecturally attractive ways. And as Kara pointed out, depending on the configuration of your shading, you can still retain the views and all of the natural daylight. Just keep out what we don't want is that direct solar gain that's striking the surface of the window. Because once that hits the surface of the window, you're toast, even if you have interior shading. So one of the challenges I think with the fixed exterior shading is it is fixed. You can't really adjust it with different seasons, and we do have quite different daylighting from summer to winter. So another option is to use an operable exterior shade, and there are lots of great examples from places around the world. Again, we haven't done a great job, or really any job, of implementing these much in Canada, but there are examples of cold climates in Scandinavia that have similar freeze-thaw cycles, similar ice, rain, sleet, snow, all of the things that we have to contend with in Canada, and they're doing just fine. So I think there's some great examples around the world that we can look to for technologies that will work in our extreme climate. There's also thinking about getting rid of heat that's in the building. So how can we do that without active cooling? And one way is to provide opportunities for cross ventilation. Now, with the building that Kara showed us before, the MERB that has sort of single-sided windows, we have really limited ability to promote that cross ventilation. So a lot of our ability to naturally ventilate is actually baked into the built form. So this is really something we need to consider more for newer builds, thinking about opportunities to have window openings on two sides of a suite can be really important as a means of passively cooling those buildings. But there are some other clever ways to do this. You can have these pivot windows where you create using a little bit of sort of micro stack effect, you can get a little bit of circulation happening. And one of the challenges, I think, is that we really restrict our window openings. So we're only allowed to open windows about 4 inches and for life safety reasons. But if we raise the window above the balustrade height, like up sort of to windows kind of up above you, then that reduces, or doesn't eliminate, but reduces that fall hazard. So we can actually open the windows more fully. So I think we also need to consider our safety regulations and how these intersect with our ability to naturally ventilate, and what can we potentially look at modifying to increase some of these operable windows. And then fans. So fans are something that I think we really don't take enough advantage of here in North America. It seems like our first response when we're uncomfortable is let me just turn on the air conditioning. There's lots of other things you can do before you get there. And as a building designer, we need to think about ways to provide all of those adaptive opportunities to our occupants in the building. And so one of the ways that we can do that is to install ceiling fans. And ceiling fans can really provide a really nice bridge between sort of your, mid 20s up to into the low 30s provide really nice comfort. I actually have a fan right behind me. I only had to turn on my AC once this year when it was 47 degrees with the Humidex. I have been otherwise very, very comfortable with my air motion here beside me. So, and there's a lot of new research on the use of fans coming out of UC Berkeley down in the States that shows that we can use fans to higher temperatures and still be safe and healthy. I think there was a lot of concern about using fans in high temperatures, but we do need to be aware that fans do add heat to the space, just like lighting or any other equipment. They are adding heat to the space. And we want to make sure that the selection of any fans are done in a way that is going to be comfortable to the occupant who's using them. I think a lot of people don't use their kitchen exhaust fans because they're so noisy and you can't hear anybody think once you turn them on. So we need to apply sort of similar principles to ceiling fans, making sure that they work well within the space, particularly in a bedroom where you want to be cognizant of noise. When you're not there, they're not actively cooling. All they're doing is cooling you. So making sure that you're turning fans off when you leave the room, because they can have real impacts on the temperatures of those spaces.
Okay, so now we've got our building, we've done our architectural measures, we've tried to make the building so that it'll be as easy to occupy without running the AC as possible. And we're considering whether or not we're going to install air conditioning. Why? Marianne and I are working on research where we hopefully can document in Canada that there is a problem that high performance buildings still have undersized or underserved air conditioning needs. Why do we still have underserved air conditioning needs when somebody like me, a mechanical engineer with a stamp, has run calculations that are intended to size air conditioning properly for this high performance building? The next step after all these passive measures is to put in active air conditioning and to size it properly. So evaluating air conditioning needs, let's maybe just flip to the next slide. In the conversation about my case study building, again, we'll talk about it a bit later, we went out and talked to a bunch of people across Canada. So we've got anecdotal stories. One of the most interesting examples we found was one of the first passive house buildings that was completed and occupied, solar heat gain coefficients of 0.5. The modeling they did during the design phase told them that they wouldn't have overheating issues. They had big operable windows. They had south-facing windows, but with exterior shading. The exterior shading was black for aesthetics. And after occupancy, they found that this building in modeling wasn't supposed to need air conditioning, regularly hits 30 to even 45 degrees Celsius indoors. It is substantially unoccupiable in the summer months, and has been consistently that way since they took over occupancy of the building. The building's not designed very effectively for retrofitting air conditioning because these really high performance windows with a very good performance in winter have this sort of tilt turn arrangement, so and are limited. So yes, that's right. We sort of thought we were going to be able to have air conditioning, like maybe if they need it, it'll be fine. And they actually have to like tape a giant plastic bag to the window to be able to put these portable air conditioners in. And so the reason that this happens is multifold. How do we come up with these poor estimates? One problem is that we underestimated the variance in the internal gains. So for those who have taken passive house training or worked with passive house, there are built-in loads associated with occupant equipment use in the PHP calculator. And then ASHRAE also has standard occupant loads, but different people use their homes differently. So when we have a high performance building, it's got a lot of insulation and it might have smaller air conditioning systems. People are used to the idea that if they create a sudden spike of heat, like I decided to bake cookies and it's today, I'm going to be warm for a minute. But what I don't expect is that my house will be overheated for a week because I took that risk for like 2 hours on a Tuesday. So there's the variability in people's temporary patterns. But then in addition, when we go to the next slide, what we found in analyzing our existing case studies was that there's also variability in people's everyday use. So the passive house load and the ASHRAE modeled loads reflect average use, but not outlier use. So if we have two people living in a one-bedroom apartment, each of them has a high graphic use intensity remote work from home job, they're without any solar gains at all, putting nearly half a ton of air conditioning load into their space just by being human beings doing their day job at their house. And they are outliers, but we still need to provide them with air conditioning that suits their needs. So there's often this narrative about high performance buildings that they don't even make terminal devices that are small enough for our loads because we've managed to dial them down so much. Whereas in reality, there is this huge bell curve of average day-to-day electrical use in suites, which correlates to heat gain in suites in the summertime, that these occupants need to be able to get out using their active systems. Not everybody's going to use them, but for people who need them, we need to be accommodating. Not, you can see it down at the end, this like long tail, but we need to accommodate the great majority of users with reasonable needs, even if some of them use more electricity than others. Another planning problem that we noticed as we were analyzing our own work was that we had used the Passive House Planning package, which is a sort of spreadsheet-based tool, as one of the ways we'd evaluated overheating risk. We had done others as well. But in that package, we realized that the whole suite temperature was being evaluated on average. So we'd taken the interior zones, the bathroom, the kitchen, all that stuff far away from the wall, and we had combined its thermal mass and its temperature gain with the exterior zones that were occupied, that were where people were sleeping, and that were where all of the thermal gains happened. So we thought we were going to have average temperatures of 26 in suite. In fact, we're seeing 28 or 31 in a bedroom, and then, very normal temperature in a bathroom, but that's not very helpful to the occupant trying to sleep. Yet another problem that caused overconfidence on our part was that the Passive House tool even sort of spit out a qualitative evaluation. It said, hey, we've run the model and we think that less than 10% of the hours in the year will be over 25 degrees Celsius. Great. Unfortunately, that was based on that average, not on the peaks. So the bedrooms and living rooms actually were significantly more than 10% of the year, but which, by the way, is 7.3 hours a day for 4 months. So that's a lot. That's a lot of overheating. And there was no limit on the amount of overheating that that tool would permit. So it could go to 45 Celsius and it would still spit that out as compliant because it only happened for 10% or less of the year. So this tool ends up substantially underestimating overheating risk while providing design teams with an indicator that they've thought about it and that they have met an acceptable industry standard. So this was a straightforward place where we realized as our design team in retrospect that this wasn't an appropriate tool and that we shouldn't have relied on this indicator. It wasn't the only thing that we looked at though. So if we go to the next slide, another thing that we did was we used like a high quality 8,760 hour simulation that did do a room by room analysis to see whether or not our building would overheat. And we even put future weather files in. So we said in 2040, if our building had no air conditioning, so the building I'm talking about now, my personal one, so Marianne did post-occupancy analysis on this building and saw it overheat. It was 17 stories. Each of the suites has windows with their solar heat gain of 0.3, and we gave everyone shades. But in our model, we were assuming that people would actually use the window shades properly. So we assume that they're home, we assume they're awake, we assume that they all understand the instructions, we assume that they're all generating that average amount of electricity use, not a peak amount of electricity use. And then the weather file we used for 2040, it turned out, was sort of an aggregate. So it looked at the average Tuesday, the 20th August that we would expect in the future. It did not do any work to try and create a representative heat wave. And so what we didn't do was evaluate whether or not our building was resilient to, it turns out, even a 2025 heat wave. let alone a 2040 heat wave. So this is something that's actually been addressed. There are better weather files now available that represent sort of a normal 2040 year that could include a heat wave. I still think that they're not, Marion, you just looked at those files with me. They don't look like they're trying to create a particularly bad 2040 year. So that file still doesn't exist. So, it is possible with our professional judgment that I still think that the easiest way to evaluate overheat risk, if you have an 8760 model, is actually to take what you think a reasonable heat wave that you want your building to be able to withstand and run that through the model. If you think, hey, I want to make sure that if it's 35 Celsius for 3 days and it only goes down to 27 at night, it does that for 3 days, I want to know what my building does. Just put that in the model, just create that and run it that way. All right, next slide. So the final mistake that I made, and I really wanted to be able to say this to every professional I've met because I was so shocked when I figured it out, is that in Ontario and the whole East Coast, when we get hot days, they're humid. And a humid hot day is substantially hotter from an air conditioning perspective than a dry humid day because the humidity all has to be condensed out of that air for us to be able to take a single degree Celsius of temperature out of it. And so on a day that I presented at 500 McNabb, which is this building that has some overheating issues that we worked on together, I was presenting about the building. It was 34 degrees Celsius, and the air conditioning load was 140% of my design day, which was 31 degrees Celsius, 50% humidity. So the engineering metric that I use gets substantially overshot when we see increases in temperature in humid environments. And so that means that when we are sizing our coils, we really have to be mindful of what future conditions we're trying to accommodate and how we oversize. And this next slide, speaks to one of the reasons we get in this trouble is that we are actually worried about oversizing cooling systems. When we oversize them, we get short cycling on compressors, which reduces their life cycle. We get poor humidity control in most conditions because we can't actually run the coil for long enough to get the temperatures down. We get uneven temperatures. So it's important when I'm talking about this to think about each individual system independently. Our in-suite terminals actually have to be right sized, sort of not too big, not too small, like a nice Goldilocks version that's still going to strip humidity out in most days, but then when running 24/7 is going to be able to provide temperature control on those hot and humid days. And then add our makeup air units where we're pulling a ton of humidity out of 100% outdoor air to be really aggressive in how much capacity we put in our coils. And that speaks to my next point, which was that I didn't really think about what happens when things go wrong. And the specific thing I didn't imagine going wrong was that I have an energy recovery ventilator that covered 80 to 85% of my cooling capacity. So the air coming back from the building should be 24 degrees Celsius. So we're going to do energy exchange. We'll take our 35-degree air, we'll get it down to 26C. So my coil only needed to do the last 2 degrees. The problem with this theory is that if I have a power outage, or what we found was more likely, we actually had some board failures because of power instability. So the unit was down for a couple of days. The building warms up, and now I don't have the capacity to cool the air coming into the building, which means that the air coming back is hot, and all of a sudden I'm only working with 20% of the peak air conditioning capacity of the building. So the fix for this is to remember, when we're trying to design for resilience, what happens if you're starting with a hot building? How long will it take you to get cool, and do you have the facilities to do it? And 2, have you thought about what happens if the air conditioning fails, but the electricity doesn't? So does your resilience planning include the idea that people still can be baking those cookies? They just can't get rid of the heat. I'm not the only person who's had this problem. In the next slide, I just wanted to note that many high performance designers got to learn this independently. This is a building on the East Coast that had exactly the same problem. So they were relying on that beautiful night cooling, enjoying their daytime adventures. And then everyone went home on a Friday. They come back to the office on Monday morning. The office and the exterior were both 35 degrees Celsius. The building was not occupiable for a whole week. It took them until the heat wave broke for them to be able to get control of the building again. So this is a real design issue and worth thinking about. And then kind of the last lesson learned from my experience in high performance buildings has been that because my systems were high performance, they were energy recovery ventilators. The staff at the buildings that were used to working on makeup air units had never seen these wheels before. They had never seen a variable refrigerant flow coil in an air handler before. And so they didn't know how to fix either one of those things. And they weren't able to troubleshoot them properly. So those factors really slowed down their identification of the problem. In some cases, they implemented fixes that were inappropriate. So yeah. Air conditioning. So many things to think about. Marian, how do we fix it?
Well, I mean, yes, one of the ways that we can not necessarily address all of those problems, but I just wanted to kind of shift gears a little bit to the retrofit scenario, because I mentioned at the beginning, we have a lot of these buildings across the country that don't have air conditioning, particularly in the rental housing and social housing stock. And so one of the things I think we need to carefully consider is as these heating systems, I know we're talking about cooling systems, but these heating systems come to the end of our lives, the end of their lives, it creates a really amazing opportunity to actually just change the way that we heat. Because if we use something like a heat pump, we can, first of all, decarbonize the heating side of the equation, but bonus, we get some free cooling in there as well. And so thinking carefully as equipment in existing buildings reaches the end of their life, like what opportunities that we have to introduce cooling where there was none before. So that's something important to consider. And another one is the use of smart thermostats. So this is based on a study that we did a couple of years ago, that we can really use smart thermostats, with additional cooling and all of this additional pressure. That's obviously more operational energy and operational carbon, but smart thermostats through the use of like occupant sensing can really reduce that load. People are notoriously bad at programming their thermostats. And so one of the nice benefits of smart thermostats is that the user interface is so much easier to use. It comes with default programming. Some of them can even learn your behavior. It's just becomes less of a thing that you need to think about. So we can just use that cooling energy more efficiently. We can also reduce our space heating and cooling loads as well through this. One of the really neat things about smart thermostats, though, is thinking about how we can use these tools to alert people to when conditions in their house or apartment are unsafe. We've just finished a study looking at older adults in Canada and their ability to cope with various things, one of them being extreme heat. And a lot of older folks don't necessarily have their physiology changes, their ability to sense extreme heat or when they're in danger can be dulled. And so we can use interfaces, smart home interfaces like this to make sure that we're keeping everybody safe.
And that ties right back into the, next lesson learned that we had as we've been really trying to roll these out, which is that a lot of the design things we've been discussing to date require interaction from occupants. And I, as a designer, had been assuming that it would be reasonably easy for people to understand and interact with my window shades, my air conditioning's thermostat, my boost button on my ventilation system, to open and close windows. A specific thing that I thought was, if it's cooler outside than inside, surely people will open their windows on their own. And it turns out that that is 100% not true. And sometimes it's because people haven't thought of it, but other times it's ragweed season, it's smoky, they can't use the window because they don't have the grip strength, and the windows are heavy. There were a lot of things that I didn't think about that meant that, again, that average occupant, we can roll out education for them, but for the extreme ends of vulnerability, it's important to create systems that have multiple layers of protection so that as people use the building, they have the ability to get dumbed down and simpler assistance. And one of the reasons that we're talking so much about air conditioning today is that air conditioning is, in that way, sort of the last line of defense for these older adults. It's hooked up to a straightforward thermostat, especially if you're in a multi-residential environment where that thermostat can be looked at by somebody remote to the property. And they can also, the adult can be alerted. The property manager can also be alerted that there are unsafe temperatures in that suite, and they can do a wellness check. So, going to the place that caused me to be presenting to everyone about this today, this 17-story tower, 500 McNabb, which we are really proud of, and which, in many ways functions as a really good example of a decarbonization project. This was a building that was at end of life. It was in such poor condition that the owner, City Housing Hamilton, was only able to actually occupy about 25% of the suites when we started working on it in 2012. We did a major retrofit in 2017. And because of the way it had been budgeted, there wasn't a budget to increase the electricity supply to the building. So we sized the air conditioning per good practice using that passive house tool, using the 8760 modeling, using the future weather files, looking at occupant behavior. And we believed we'd created something that wasn't going to have overheating problems for this reason, even though we were only able to add as much air conditioning as was permitted within the existing envelope of the electrical supply. And we talked this through with the building owners. The building owner knew this wasn't a fully air-conditioned building when we turned it over. So what were the things that we learned that went wrong that I want you all to, keep in mind when you're thinking through whether these kinds of solutions work for you? So like one of the problems was that the mechanical system was new to everyone. To be able to have that low electrical connected load, we did our cooling centrally, and then we ducted it to each individual suite. And we gave each suite a variable air box so they could have more or less cooling depending on what they wanted. That was new to operators. So when those vents actually failed, they didn't notice. So we were getting overheating in a suite sometimes just because the damper had closed, or because a sensor in the damper had failed, and they weren't able to figure that out because the people we trained had been flipped over. Initially, people were complaining a lot on the operations side because the temperature of the makeup air unit fluctuated a lot. So to deal with that, there was an HVAC tech at some point who locked out half the cooling capacity. So that way we didn't see as much variation because we weren't actually getting as much cooling. And that worked until we had our first heat wave. And then the system wasn't outputting enough cooling. But because it was so small in the first place, it never occurred to the owner to think that the system could be underperforming. So we ended up with a building that was overheating. It was very difficult to diagnose. We actually had to go back to first principles and run the calculations to prove that the air conditioner should have been able to do more. And all of this had to be done kind of on an emergency basis because we hadn't designed the windows with any spot to be able to put that temporary air conditioning in. So we were, again, taping giant pieces of plastic to windows to be able to give spot air conditioning to really, there were only about 3 residents who had significant health problems and wanted additional air conditioning, but it was really hard to get that for them. And if we had planned our building envelope with room for additional spot cooling, that could have been, like, that operational pressure could have been alleviated. So, looking at it, it was actually, she says, somewhat of a success. We were regularly maintaining temperatures 26 and under in most suites most of the time with half the design air conditioning load, which was wild. But in some circumstances, the temperatures in some suites would end up at 27, 28, 29. And it's interesting because the people who could follow the instructions we'd given were, even in those conditions, able to keep their temperatures low, but not everyone can. And as an equity issue, it's becoming extremely important for me to say out loud, everyone deserves air conditioning, even if they can't figure out how to operate their blinds in exactly the way that we prescribed, even if they can't make their ceiling fans work for them. So a lot of lessons learned on how that project went forward. The biggest one being that a lot of spare capacity on the air conditioning side would have significantly alleviated these operational concerns, even though they would have increased the building's energy used in peak periods. So, for want of that spare capacity, it's been a lot more difficult for the operator to get their hands around. Marianne, any other thoughts about lessons learned here?
No, I think you've covered it really well. I'm just cognizant of the time. So
All right, I'll let you keep going.
I'll wrap up. Yeah. Yeah, no, this is
Today's video
really
I'll
good.
be showing you how to use an
Oh, sorry, I don't know. Okay, yep, all good. Yeah, I think, Kara's done a wonderful job of summarizing all of the lessons. I just wanted to throw one more out there, which might seem odd coming from two engineers. But one really important thing to think about is how we design and operate our buildings to really promote a sense of community. Dealing with overheating risks is not just a technical problem, it's also checking on your neighbors, making sure everybody knows who is maybe having those health challenges that need some extra attention, and making sure that everyone is safe during these events. So it's not just something we should be considering in the moment, but something that we should be really building up over time. Do you want me to speak to this one, Kara, or do you want to?
No, I think that this. Yeah, go ahead, actually.
Yeah. No, I think one of the really big challenges I think in our industry is there's just not much of a feedback loop. You might learn a little bit when something goes off the rails, but we really need to do a better job as an industry taking these lessons, all of the wonderful lessons that Kara shared today, and shouting them from the rooftops. Like, we should all be learning together so that we're not making these mistakes over and over again. I'll just plug really quickly, we've been working on a study on how we promote reflective practice in the building industry and what are the standardized ways we can sort of build these into existing workflows, because nobody really thinks about this at the outset of a project. Of course, everything's going to go perfectly on budget, on time, all the systems are going to work as they should. The reality is that never happens. And so we need to think at the beginning of a project about investing time in learning and commissioning and doing all of those things at the end. And we're also, in our research group, we're working on developing a standardized residential post-occupancy evaluation tool that we can use for exactly this purpose, that all of that data will go into an open source database so we as an industry can learn what the critical issues are. Just to summarize very quickly, I'm going to actually go right ahead to our key takeaways. So as just to sum up where we're at, as Kara pointed out, first we need to really understand overheating risk and use real loads, experiment with different weather files, think about what future situation this building is going to have to live through, and all of these people need to live through. And then I think the way in which we address that overheating risk needs to be ordered. First, we want to do everything passively that we can to keep heat out of the building. Then if we're a little uncomfortable, let's turn on a fan. Don't reach for the AC first. Work with fans as much as you can and make sure that's integrated into your design. Then bring in the AC, but only if you've done all of the other things on the list. And then of course we need to follow up and find out how this all went in the end again, so we can learn together as an industry. So Kara, any last words?
No, I think that's glorious. You nodded to ventilation risk. I lied. I do have one, which is you nodded to, sorry, natural ventilation. We haven't included slides on this, but I do like to point people to just even the ASHRAE design guide, which has got guidance on how big the operable area for a window needs to be to achieve ventilation. And just a little bit of thinking about 2 openings is better than 1, right? Double-sided is the best, but even just having 2 windows creates like drum ventilation. So not defaulting to there is a window and it can be opened, but going to the next step of looking at the amount of operable area and seeing if it fits into the guidance that already exists in the legislation under ASHRAE's natural ventilation can get you a long way on that, integrating that particular passive low carbon strategy, which is incredibly important because when the power is out, the air conditioning won't be on. So those windows become an enormous part of the resilience strategy. Okay.
Okay, we'll wrap it up. Sorry, Sue.
No, it's perfect. Thank you guys so much. That was such an informative presentation. You covered all of the really challenging complexities of this, but also offering solutions at the same time. So it's a really well balanced presentation. If there's any questions that the audience have, please put them in the chat. I noticed there's one there already. Just one question for myself first. We have a lot of municipal staff here with us today, and I'm just wondering for folks who are working with aging social housing stock, do you have any suggestions on the kind of the most actionable entry point for improving health and comfort without a full retrofit?
Karen, do you want to jump in or do you want me to start?
So the question is recommendations for improving health and comfort without a full retrofit.
Yeah,
So
and like
ceiling
easy entry
fans.
points. Yeah, yeah.
Ceiling fans, ceiling fans, ceiling fans. The one behind Marion is, I'm surprised that it's not too noisy for her to present. And you're tripping over them and they don't provide even coverage. You can get such good 3 degrees Celsius is just like the guideline improvement in thermal temperature experience from overhead ceiling fans. And they provide heating load reductions as well by destratifying spaces. So I like that as one. Thinking about spot cooling is the other one that I would recommend. Like think through how the building is being used and if there are specific spaces that adding a single mini split would help if you don't have the budget for a full air conditioning retrofit.
Then once
Marianne,
you do
thoughts?
those two things, start thinking about the exterior solar shading because really we've got a lot of balconies. We can mount those too. It doesn't have to be a terribly expensive solution. And I will just circle back to I think the education. I think a lot of people don't realize how dangerous heat can be. And so one relatively low cost thing to do is just to promote that education within the building and that community building, keeping an eye on folks that are maybe a little bit more vulnerable to that extreme heat.
Yeah,
One
I think that's
question. No,
incredibly
go ahead.
important.
Yeah.
Someone pointed me to a resilience study comparing Seattle to Vancouver and comparing different neighborhoods to each other, and the mortality had very little to do with active air conditioning, even though most of the deaths were in places that didn't have active air conditioning. It had a lot more to do with social integration, whether or not people had access to community supports. So that is an intrinsic part of the health and safety protections that we provide people.
I think we're in a unique position as a social housing provider to be able to do both the social and the technical side. And that's really key.
One question in the chat. Have you considered the technology, I'm not sure if I'm pronouncing it right, immersion, which can cool a building with 1/15 of the amount of electricity? And this technology was developed at U of T and is now commercially ready. Any familiarity with this?
So I know this is going to make me sound crazy. Yes, this is very cool. So there's a question of what, and then there's the question of how. I love this as in how. The important thing is did you provide enough air conditioning? And if you can do it in a more energy efficient way, that is incredibly great. But don't wait until you can install immersion. If this particular technology, if the need is there to provide health and safety benefits now, like that's more of my point is that. I have in the past been distracted by trying to do this in the most energy efficient way possible. This is a great technology to do that. But let's remember that this is a life safety issue and we need to provide people with appropriate air conditioning, whether or not it requires electricity to do it.
Another question, any comments on the idea of free cooling from bypassing heat exchangers and HRVs, ARVs for buildings that don't have air conditioning when outdoor air cools at night?
Again, really love it as a easier, lower energy way to get cool air into buildings. One key consideration in humid climates is it is often very humid when it is cooler at night. And so bringing that in without dealing with the humidity can cause comfort issues in the daytime. So that playing with the PHS tool is something I recommend, that CBE calculator. And what you see is that when you let the humidity drift above a certain level, our physiology can tolerate much lower temperatures before we start being in danger because our sweat doesn't cool us. So I like it as a shoulder season measure, but it doesn't address peak heating events. David McMillan, yes. Yes, I love an oversized cooling coil in an MUA. The one thing for social housing operators, another lesson learned we didn't share was that we did have problems with people propping their doors open because it was cooler in the corridors than in their suites because they had windows in their suites and not in the corridor. So thinking through those operational issues, if you decide to add air conditioning to a corridor, just being in conversation with your building operator because they may not love the corridor being the cooling center. And it may pose fire risks if people prop their doors open overnight.
And also depending on your ventilation strategy, that may or may not be a great idea. Because if you do have ventilation in the suite, your suite door is probably going to be pretty well sealed. And then so your cooling in this air is actually not getting its way into the suite. So just thinking about where that air is going. And there's a lot of other issues beyond security, like pest control, noise, smoke and odor transmission, all of these other things that would be fairly negative consequences if people were having their doors propped open.
Can I let you do that policy question?
Yeah, I'll just read it out. So from a policy angle, can both of you comment on the status of maximum indoor temperatures bylaws, similar to minimum temp bylaws for winter for residential buildings based on your research?
Yeah, I've been thinking a lot about this. I think it's really challenging. I think we need it from a health and safety perspective. We absolutely, everyone deserves the right to be healthy in their home. My concern is that a lot of those costs are going to end up contributing to housing precarity and potentially pushing people out of their homes. And so I just think it's a very tricky issue that I don't know if we've thought all the way through to the end. Who's going to pay for this? Who's going to support the building owners in that rollout? We need it, but what does the implementation look like?
And as an engineer, I just like I desperately need them to stop saying maximum temperature and start saying a design temperature of X at Y temperature, right? Like 26 indoor when it's 31 outdoor and the sun is shining. Okay, as an engineer, I can achieve that. It goes to 42. We can't oversize an air conditioning system to meet a minimum temperature in the space at all times in the way that we can when we're talking about heating. And so there, I think because heat waves are unpredictable and an ongoing increasing issue, just deciding on a number and saying it's the number is going to exacerbate the issue that Marianne just noted in terms of the cost for people to put in compliance systems.
I do think the other issue, there's the variability of the outdoor conditions. There's also just the variability of what people can cope with. And the fact that an air temperature doesn't have anything to do with the mean radiant temperature around you, the relative humidity, the air motion. There's lots of different sensations you can have at 26 degrees. Some are just fine, some are unhealthy. And so distilling it down to one temperature, I get why we need to do it from a policy and simplicity perspective, but I think there's some challenges there as well.
One quick follow-up, and then we'll probably wrap up after this, but a follow-up question. Does energy, water reporting and benchmarking approaches, which is getting more mandatory help? Another policy type question.
I think the more information we have about our building stock, the better. As a researcher, I find it incredibly frustrating that we have so little data on our building stock. It's hard for us to know where to go from a policy direction. A lot of it is anecdotal, or we're hearing from designers and residents about challenges in buildings. And so I definitely think we need to invest more in learning more about our buildings as an industry.
Okay, great point to end on. Thank you both so very much. Great presentations today. Much appreciated.
Thanks for having us. That was fun.
Okay.
Thank you
Take
so much,
care.
guys.
Bye, everyone.
Everybody.